Hello again. Suppose I have an object just out in space, removed from all other forces, and it's just moving along in a straight line. According to Newton's first law of motion, it will just keep doing that. Now, if I want to speed it up or slow it down, I have to apply a force to it, so I could push on it and speed it up, push the other way and slow it down. But what if I want to change its direction? So it's moving along like this. I have to apply a force perpendicular to its motion. Then I can change its direction. So see again, it's moving along like this. I want to change its direction. If I push along its direction, I can speed it up or slow it down, but that doesn't change which way it's going. If I want to change which way it's going, I have to apply a force in some other direction, say perpendicular to its direction. Now suppose it's moving along like this, and I apply a force perpendicular, and then a force perpendicular, and then a force perpendicular. Notice it keeps changing direction. And you can imagine if I just keep applying a force perpendicular to its direction of motion, if I continually do that, I eventually can imagine this object will move in a circle. And that is exactly what happens. And that force that keeps an object moving in a circle, we call centripetal force. So for example, if I have a ball at the end of a string and I pull on that string, giving the ball some velocity v, and I apply some force F, then I can keep that ball moving in a circle. And in that case, we would call this the centripetal force. The force keeping this object, in this case the ball, moving in a circle. So F centripetal force is force pointing to the center of a circle that keeps an object moving in a circle. Force pointing toward center of a circle that keeps an object moving in a circle. Notice it's not a new force. For the case of the ball, it was my tapping on it constantly that would be moving it in a circle. For the case of the ball on a string here, it is the tension force. So I'm pulling on the string and we call that tension. This could, for example, be looking at, we could be looking down on a road, suppose, instead of the ball on the string, get that out of your mind. We're looking down on a road, and this is a car going around a curve. So now we're looking at a car, we're looking down on it, and it would be the friction between the tires and the road, pointing toward the center of the curve of the road. That keeps the car moving in the circle as it goes around the curve. In this case, the friction is providing this centripetal force. So it's not a new force. Centripetal force isn't a type of force. It's just saying it's when the force is causing something to move in a circle, we call it centripetal force. Now, since the object is not moving in a straight line, it must be accelerating. And which way is it accelerating? The acceleration is in the direction of the force, and we call that the centripetal acceleration. So the centripetal acceleration is the acceleration pointing to the center of a circle of an object moving in a circle. Acceleration pointing toward center of a circle of an object moving in a circle. So I know there's an acceleration because if there were no acceleration, the object would be moving in a straight line, according to Newton's first law of motion. So if I were to let go of this string, for example, this object would fly off in a straight line like that. Now, how big is this force? I'm not going to derive it. I'm just going to state for you that the amount of centripetal force you need for an object to move in a circle is mv squared over r, the radius of the circle, where you've got a circle here, object moving in a circle, this is its radius, v is the tangential velocity as it goes around the circle, and this is how much force it takes for an object moving at velocity v with mass m, radius r to move in that circle. Sometimes we may want to express this in terms of our new angular coordinates we've just learned about. So remember that v is r omega, so we could write this as m r omega squared over r. This would be r squared omega squared. One of these r's, we cancel this one, and so this would be m r omega squared. So you need to memorize that m centripetal is mv squared over r, or mr omega squared. You should know both of those, so memorize those. We're going to use those and need to know those. Those are our relations for centripetal force. So I'm going to do 2 or 3 examples for you. Let's do that now. So first case is a car rounding a curve. So we're looking down on a road. It's a flat road, and that road has a radius of curvature of 50 meters, and a car is rounding that curve. So looking down on the car here, I'm just drawing the tires so you can get the perspective. The car is going with a speed v equal 30 miles per hour. That's 13.4 meters per second. And I want to know what mu is needed. What mu static is needed for this car to successfully round this curve. So what's keeping the car moving in a circle, because it is the frictional force, mu static, between the tires and the road. You say, why is it mu static? Because the car is moving. Well, even though the car is moving, at any given point, the tire and the road are at rest with one another. So here's the tire, and here's the road. If you're not skidding, the point where the tire comes in contact with the road is actually at rest. If it were not, you'd be skidding. So this actually mu static is the appropriate mu to use here. So we've got frictional force between the tires and the road is what's keeping the object moving in a circle. So here's the center of the circle, or this is the radius of curvature of this road. Frictional force is the source of our centripetal force. So we've got that frictional force is mv squared over r. How much frictional force do we have? Well, if I looked at this edge on, here's the car, here's friction, there's a mg down, a normal force up. We know friction is mu n. In this case, n is just mg, so friction is mu mg for this case. It's not always that, but it is for this case. So I've got mu mg is mv squared over r. The m's cancel, and mu is v squared over rg. That's our 13, let me write that big enough you can see it, 13.4 meters per second squared over the radius of the road, 50 meters squared. G is our 9.8 meters per second. Quantity squared. That turns out to be a very reasonable 0.366. But you know, if it's snowy or rainy, that may not be enough. So we make the roads not flat so that you can round the curve. So there's our first example. do another one for you. Here's a case of, say, a roller coaster at an amusement park. So we've got a car heading up over a curve like this, and up at the top of the curve, we want to know what's the minimum speed, V, that the car can go and round the curve. So I've chosen this curve to have a radius. It's just a roller coaster of 5 meters, not the 50 meters like in the previous example. We need this car to go in a circle. So there has to be some centripetal force like this, some centripetal force pointing down. What are our options for that centripetal force? That centripetal force can be due to gravity, mg, and it can be due to the normal force of the track pushing on the car. What I'm asking is, what is the minimum speed? The minimum speed will occur when the normal force goes to 0, when this would just be falling off. So when this is just falling off, this N vanishes. And we just have mg as all of the centripetal force. So our minimum speed occurs when our centripetal force, F, that's not friction, that's centripetal force. When our centripetal force, F centripetal, is mv squared over r, is given by just gravity. mg is mv squared over r. This gives me v is gr square root. That's 9.8 times the 5 meters square root. And that turns out to be 7 meters per second, or about a little over 15 miles an hour. And your car will stay on the track if you're on your roller coaster, which is presumably something you very much desire. So you want to go faster than that, so you're not at the very, very minimum. One more example of centripetal force. It's a little more challenging mathematically. Suppose we have a mass on a spring, a string, that's going around in a circle like this. So it's going around like that. And this is a 30-degree angle. And let's see, I want to know the velocity if this radius is 30 centimeters. So about like that. So that this just goes around in a nice circle. So you've got a string down like that, and this is going around like that. All right. So we need a centripetal force this way, pointing toward the center, because the center of the circle is that way. What we have is a tension this way. The other force we have is an mg of this mass, m, down. This is 30 degrees, so this is 30 degrees. If this is 30, then what we have available to us isn't this full tension, but this is T sine 30. In this direction, we've got T cosine 30. And so now what I know is in the vertical direction, these forces have to balance. T cosine 30 up has to equal mg down. And in this direction, the T sine 30 has to give me my centripetal force. So I've got T cosine 30 has to equal mg, and T sine 30 equals mv squared over r. Now I've got two equations and two unknowns. So I'm going to divide this equation by this one. That's an algebraic trick that people use. So that will cancel the t's. So I've got t sine 30 over t cosine 30 equals mv squared over r divided by mg. The t's cancel. Sine over cosine is tangent. I've got tangent 30. The m's cancel. And algebraically, this is v squared over rg. So v is the square root of rg tangent 30. See, that one's a little tricky. You might have to practice that one. I plugged in all those values, 0.3 for r, 9.8 tangent 30, and got 1.3 meters per second. So there you have it. There's our last example, and you can practice this at home.